Hello, and welcome to Lesson 6 of this Introduction to Calculus with Wolfram U. Our topic for today is continuity. So let's begin with a brief overview of the idea for today's lesson. Begin by recalling that if you have a polynomial like this one over here, then its limit at a point is simply the value of the polynomial at that point. So if you look at the polynomial f of x, then I simply replace x by a and I get the limit of f of x as x approaches a. So that's a very special property of polynomials and similar functions, namely that their limit at any point is just the value of those functions at that point, and such functions are called continuous. So a continuous function is one for which the limit at a point and the function value agree. So this lesson will give examples of continuous functions, functions that are not continuous, so-called discontinuous functions, and we'll also give a nice application of continuity. So let's begin with the definition of continuous functions in a formal way. So a function is continuous at a point a if the value at a is equal to the limit of f at a. So for a function to be continuous, three things must happen. First of all, it must be defined at that point. The limit must exist at that point. And that's not enough. The limit must equal to the value of the function at that point. So the equality is a very important condition for continuity. So very informally, a continuous function should have no gaps or breaks in its graph. So if you draw the graph of a function and it looks continuous, it's got no gaps or breaks, then in fact that's very likely to be a continuous function. So for example, here is a function of x as a polynomial, and its value at 1 is the same as the limit. You plot it, and sure enough, there is no break in the graph, so that is a continuous function. So that's just a simple way to tell whether a function is continuous or not. Okay, so some simple examples. So polynomials and rational functions are continuous wherever they are defined. So here's a polynomial f of x and a rational function g of x. F is of course continuous at every point, but g is continuous everywhere except at -1 where the denominator is 0, so it's not defined. So here's a plot of f of x, nice and continuous, and a plot of g of x which has a problem, a discontinuity at -1. Okay, so next let's talk about functions which are not continuous. So a function that is not continuous is said to be discontinuous at that point. So here are two examples, f of x and g of x. Now, if you think about f of x, there's a problem at 1, and if you find a value at 1, sure enough, the answer is indeterminate. So that function has a discontinuity at x equal to 1. Now, what's happened with g is that we've changed the value at 1, hoping to fix the problem, but that's still not good enough because the limit as you approach 1 is -3, while the value is -2. So if you plot the functions, you see that f has a problem at 1, which you can't really see over here, but that's the fact from the definition, whereas g did not quite fix it because you chose the wrong value at that discontinuity. So of course you're going to fix it, but the whole point is to construct examples where things can go wrong for continuity. Okay, a second class of examples here is a piecewise function f of x, and clearly that's problematic at 0 because you're dividing by 0, and that's the floor function g of x. So f clearly has a discontinuity at 0. You can see that. Got infinity over here and 0 over there, whereas g is a bit more complicated. It's got discontinuities at all integers. So for example, at 0, it's indeterminate, the limit, and the value at 0 itself is 0, so clearly there's a problem at that point. So here are the functions. F only has a problem at 0, while G seems to have many more problems in its graph. Okay, so although the flow function is discontinuous, it does have one nice property, namely that if you approach it from the right, then things are okay, but they're not from the left. So let's see that for the flow function. If you try and find the limit from the right, from above, for the flow function at 0, then it's okay. You get back true. But if you try and find from the left, then it is not okay. So the plot clearly says that you have issues at all the integers, but in fact you have a function, the flow function, which is continuous from right at every integer, but not from the left. Okay, so root functions are also very similar to polynomials because they're continuous everywhere in their domain. So wherever they're defined, you're okay. So here's a square root function, f of x. That's continuous wherever it's defined, namely when x is non-negative. But at -1, it's got an imaginary value I, so one cannot really talk about continuity at that point. So here's a graph, and as long as the function is defined, there is no problem at all, it is continuous. Okay, so trigonometric functions are pretty simple. The sine function and the cosine function are both continuous at 0, and in fact, they are continuous at every point. So here's the graph of each of these functions. They're clearly continuous, there are no breaks. And one way to prove that might be to use the addition formulae from algebra, from trigonometry, which can be used to show that these functions are actually continuous at every point. On the other hand, the tangent function has a problem because the denominator is cosine, so it is not continuous whenever the cosine is 0. You can see the problems over here. At every place where cosine becomes 0, like pi over 2, etc., there are problems with the tangent function. Okay, so if you want to go further, then one needs the laws of continuity. So just like you have the laws for limits, you also have the laws for continuity. So you have the sum law, which says that if f and g are continuous, then so is f plus g. You have the difference law, which says that f minus g is also continuous if f and g are so. The scalar multiplication law, which says you can multiply by constants and still get continuity. The product law for products, and the quotient law for quotients. So together, they give you a nice way of showing that fairly complicated functions are in fact continuous. So here's the function f. It looks pretty complicated, but then you think about it and say, oh yes, cosine is continuous, so is sine. Now you're dividing over here, you're adding over there, etc. So by the laws of continuity, this function is continuous. And if you find the value at pi, the answer is the same as the limit at pi. So that's a powerful way of showing that a function is continuous, namely to apply the laws of continuity, just like one could apply the laws of limits. Okay, so a slightly harder problem is what happens if a function is a composition, so it's f of g of x. Well, in that case, you simply let the limit go, so to speak, inside the bracket, and if you still get the same answers, then you're okay, and that's exactly what's happening over here in this case. So basically, you have f of x defined as cosine of a polynomial, but cosine is continuous, so is a polynomial, and this function is the composition of trigs and polynomials. If you look at the graphs, everything looks fine, and in fact, the function is continuous. So the point is that given a composition of functions, you can basically show that they're continuous by looking at each piece separately. So in this case, you looked at x squared minus 7x plus 10, and you looked at cosine, and then we were done. Okay, so we are almost done with today's lesson, but one last important theme is that you can actually apply the idea of continuity in practice to find roots. So the theorem that helps to do this is called the intermediate value theorem. That means the theorem for values between two values. So what it says is that if you have a continuous function f on an interval a to b, and you have any number n between f of a and f of b, then you will have a value somewhere in the middle such that f of c is equal to n. So basically, a continuous function will take every value between any two of its values. Of course, one must assume that they are distinct to get some kind of interesting behavior, but basically, you can assume for continuous functions that they take every value between any two of their values. So let's try and find the root of this rather complicated looking polynomial, f of x. It's a cubic polynomial. Now you want to find root between 1 and 2. So what you do is, you first of all evaluate at 1 and 2. You find that it's negative here. It's positive there. So because the function is continuous, and because 0 lies between those two numbers over here, then there must be a root in the interval. So using the intermediate value theorem, you can now check by the plot or by solve that in fact there is actually a root. And that root in this case is about 1.63334. So people who try and solve equations will often apply this theorem to try and find a root of a function. So that's a very powerful application of continuity. It's not just a theoretical concept, it's a very powerful practical concept. Okay, so we are done for today's lesson. Let's summarize. So basically, continuous functions are very common in the real world. And in fact, most functions you'll meet are going to be continuous. There really is no problem at all. We did see some examples, but they were somewhat artificial in some cases, and you don't need to worry about them mostly. Informally, a continuous function has no gaps or breaks in its graph. If you look at polynomials root functions, they're continuous wherever they are defined. That's no issue for polynomials, but for root functions like the square root, you don't need to worry about where they are defined. Now, rational functions and trigs are slightly harder. They may or may not be continuous. That depends upon the kind of way that they have been set up. And finally, the intermediate value theorem is a very powerful way to find the roots of functions. So that's the end of the discussion of continuity for today. And in the next lesson, we'll begin discussing differential calculus by using limits to define so-called derivatives. And that's where calculus really becomes useful in a very profound way. So next lesson is a time when we start looking deeper into calculus. But before doing that, do review today's lesson, try and solve the exercise, and be ready for the next time. It was great to present this to you. Thank you very much.